Inside your body, right now, a microscopic war could be raging. And in this war, our secret weapons are antibiotics. But they don't just carpet bomb the enemy. No, they're way more like secret agents, sent on a mission to sabotage the enemy's most critical infrastructure from the inside. So let's dive in and see exactly how they pull this off. See, to stop bacteria, we don't just kill them outright. The real and much smarter strategy is to shut down the tiny factories they absolutely need to live, grow, and multiply. These factories are called ribosomes, and today we're going to see exactly how our antibiotic saboteurs bring their entire operation to a grinding halt. Okay, so first things first, let's get to know the target. We're talking about the bacterial protein factory, which scientists call the ribosome. Just think of this machine as the absolute heart of the bacterial cell. It runs 24/7, building all the essential proteins for structure, for function, for making more bacteria. Without this factory pumping out products, the bacterium is basically dead in the water. And that total dependency, well, that's its greatest weakness. Because this factory is so essential, it becomes this massive glowing target. If you can shut down the ribosome, you shut down the bacterium. It is the ultimate weak spot, and antibiotics are precision engineered to hit it. So, before we send in our saboteurs, we've got to do some reconnaissance, right? How does this protein factory actually work when everything is running smoothly? It's basically a three-step process, just like a real assembly line. First up is initiation. This is where the machinery gets set up around the genetic blueprints, the mRNA. Then comes elongation, where these little delivery workers called tNMA bring in the raw materials, amino acids, to build the chain. And finally, termination, where the finished protein is cut loose and sent on its way. Simple, efficient, and absolutely vital for the bacteria. All right, now for the fun part. Let's meet our first team of antibiotic saboteurs. Their specialty? Making sure the factory can't even open for business. This class of antibiotics is called the aminoglycosides, and their entire game plan revolves around messing up that crucial initiation phase we just talked about. Now, what's really cool is that the ribosome is made of two main parts, a small one called the 30S and a big one called the 50S subunit. Aminoglycosides go right for that smaller 30S piece. They basically prevent the two halves from locking together correctly, so the factory can never be fully built to even start the job. And it's not a one-size-fits-all attack either. Different agents in this class have their own special moves. Streptomycin, for example, messes with the very first assembly step. Kanamycin and tobramycin let it get a little farther, but then they block the final formation of the complete factory. And hygromycin B, well, it has a particularly nasty trick. It actually distorts the machinery, causing it to misread the blueprints and build completely useless, garbage proteins. Okay, so that's how you stop the factory from ever starting. But what if it's already up and running, churning out proteins? Well, let's bring in our next group of saboteur. Meet the tetracyclines. Their strategy is beautifully simple. Create a massive traffic jam right at the factory's loading dock so no new materials can get in. Their method is so direct. They bind to a specific spot on that same small 30S subunit called the A site. You can think of the A site as the docking bay for those tRNA workers carrying amino acids. By binding there, tetracycline physically blocks the entrance. No new parts can be delivered, and the whole assembly line just grinds to a halt. So yeah, it's a direct physical roadblock. But what's really genius is how they get there in the first place. Tetracyclines actually hijack the bacteria's own transport systems to pump themselves into the cell, reaching a concentration way higher than what's outside. They literally turn the enemy's own logistics against it to make sure the blockade is overwhelming. So we've blocked the startup, and we've blocked the loading dock. What else is there? Well, our next saboteurs, the macrolides, have a completely different idea. If you can't stop the product from being made, just stop it from leaving the factory. This is wild. Instead of targeting the small subunit, macrolides go for the large 50S subunit. They wedge themselves right into the exit tunnel where the newly made protein chain is supposed to come out. And the result? A massive product backup. The chain can't move, no new amino acids can be added, and the entire production line just freezes up. And other antibiotics also target this large 50S subunit, but in different ways. While macrolides, like erythromycin, clog the tunnel, others, like lincomycin and clindamycin, act more like a monkey wrench in the gears. They directly shut down a crucial enzyme, the very tool that links the amino acids together. So one clogs the exit, the other breaks the welder. Same target, totally different tactics. Now, all these methods are effective, but there's one that is just so cunning. It doesn't just block or break the machinery, it actively deceives it. I mean, what if you could trick the factory by slipping it a counterfeit part? Meet puramycin. It is an almost perfect molecular mimic of a real tRNA worker molecule. It's an imposter, a counterfeit component designed to look and feel exactly like the real thing to the ribosome's machinery. So here's how the deception works. The puramycin imposter gets into the factory's loading dock, that A site. The ribosome has no idea, so it grabs it and attaches it to the growing protein chain. But because puramycin is a fake, it's unstable. It immediately breaks the connection, causing the unfinished, totally useless protein to just fall off and float away. The sabotage is so effective it causes a complete and total shutdown. Okay, so we have all these incredibly powerful saboteurs that can shut down bacterial factories. But that leads to a really important question. If they're so good at this, why don't they shut down our factories too? Well, the answer comes down to a brilliant principle called selective toxicity. See, it turns out our cellular factories, our ribosomes, are a different model. They're called 80S ribosomes, while bacteria use the 70S model. It's a subtle but absolutely critical difference in their structure. Our antibiotics are like keys designed to fit only the 70S bacterial lock, leaving our own 80S machinery completely unharmed. And that really is the central theme of this entire microscopic war. The whole strategy, as this quote points out, relies on targeting those unique components, the 30S and 50S subunits that make up the bacteria's special 70S ribosome. That specificity is what makes them such powerful medicines. These molecular saboteurs are truly ingenious, amazing feats of biochemical engineering. But the war isn't over. Bacteria are constantly evolving. They're learning to recognize our agents and fortify their factories. And this leads us to the final critical question. As the enemy adapts, what new weapons, what new forms of sabotage will we need to invent for the next fight?